This is Navodit Aditya. Welcome to my channel NAditya83. Today we are discussing an important topic of rotational mechanics, that is rolling motion. In rolling motion, we are actually speaking about rolling without slipping. That is the topic that should we focus on. In rolling without slipping, we actually want to mean that a spherical body is rolling smoothly without slipping on the ground. There is enough friction to prevent the body from slipping. Actually, the rolling motion, if we look into, can be thought of that a body, suppose a spherical body is like this. It is rolling on the ground. It has a radius r and it has a center. It will move forward on the ground with a certain velocity, and it will also rotate about a certain axis which is passing through its center. So we can see that the rolling motion is actually a combination of translation plus rotation. Rolling motion, so we can thought of as a combination of translation and rotation. Now this translation is with a velocity vc of the center of mass moving forward, and this rotation is about an axis through the center of mass with an angular velocity omega. In short, we can write down it as translation of center of mass with velocity vc and rotation about an axis through center of mass with angular velocity omega. Now, one of the most important concept of rolling without slipping is that the distance moved forward by the body, if be s be distance moved by center of mass, and if theta be the angle rotated in the same time, then they are related by s equal to r theta. This is the governing equation of the rolling motion. So let's repeat it once more, that s denotes translation, distance moved by center of mass, and theta is the angle of rotation rotated about center of mass with angular velocity omega. So they are related by s equal to r theta. Differentiating with respect to time on both sides, we get ds dt equal to r d theta dt. By the problem, we know that ds dt is the velocity of the center of mass and r d theta dt is the angular velocity omega. So this is the second most important equation of rolling motion, that is, again we are repeating, it's rolling without slipping. Again, if we go on differentiating for the second time with respect to time, that is ddt of vc, r being a constant is left out of the differentiation. So we get acceleration of the center of mass is equal to r alpha, where alpha is the angular acceleration about an axis passing through the center of mass. For information, I am writing down AC as acceleration of center of mass, and alpha is the angular acceleration about center of mass. With these equations in hand, we move forward for getting the velocities of any point on the periphery of the sphere which is rolling with respect to the velocity of the center of mass. So, first we are discussing the kinematics of rolling motion. In many books and in of all the common handbooks, we get an idea about the kinematics of rolling motion. But here I will do a vector calculus treatment to go forward and see what's happening actually. Suppose this is the sphere. It is rolling without slipping on a ground where there is enough friction to prevent it from slipping. It is moving with velocity vc about the center of mass. Suppose we have to find out the velocity of any point A which is on the periphery. Let the velocity that we have to determine be VA vector. VC, it being in the x direction as we have shown, and this is the y direction. VC has the vector I cap denoted with it. For all practical purposes in this motion, we will consider omega to be in the negative z direction. So omega is a vector here with its vector being shown as omega minus k. Again I am repeating that we are giving a vector treatment of omega. Actually omega is a vector quantity and it is denoted by omega in the negative z direction with omega minus k. So if I have to find out the velocity of A with respect to C, we shift this vector like this, VA. We complete this triangle, that is the vector triangle, and denote it by VAC. So the velocity of any point VA is given by the vector sum of VC plus velocity of A with respect to C. Please keep in mind this equation which helps us to find out the velocity of any point when we are given the velocity of center of mass. Now we have to check what is this VAC. Suppose a vector, let us consider any vector A which is rotating with a velocity, angular velocity omega about a center with the radius vector being r vector. So we can say from that equation that dr dt is omega cross r. Any vector rotating about a point with a radius r with an angular velocity omega can be written as dr dt equal to omega cross r. Similarly, VAC can be written as omega cross position vector of A with respect to C. So this turns down to VA vector equal to VC vector plus omega cross RAC. This is the velocity equation. To find out the acceleration equation, we differentiate with respect to time and get ddt of VA vector is equal to ddt of VC vector plus ddt of omega cross RAC vector. ddt of VA vector, as we know, is the acceleration of A, point A. ddt of VC vector is the acceleration of the center of mass, plus ddt of the cross product of these two vectors. Now we have to deal with this vector cross product to come to the solution. So we have got